13.3, derivatives. The idea of derivative is a refinement and extension of instantaneous rate of change. With this in mind, let's review our definition. For a function f of x defined at a, the instantaneous rate of change of f at a is given by the limit as x approaches a of f of x minus f of a over x minus a. So we have a slope, and we are looking at x getting closer and closer to a. Now, there's another way to phrase this. X approaching a is the same as the distance between a and x approaching 0. Let's look at what that means on a graph. So here's my point, which corresponds to a, and here's my arbitrary point, corresponding to x. The distance between a and x is this length right here. Let's call it h. Then, in other words, x minus a is equal to h. Okay, now that would be this piece of a triangle. The triangle that would be useful to look at would have these two sides. Let's look at the definition of the vertical side. Now, we know that the y values are what define the vertical side, so this must have side length f of x minus f of a, because remember, this point up here was defined as x comma f of x. Now, if we were to think about our slope would have been m equal to f of x minus f of a over x minus a. But we just said that h was x minus a. H is that distance between x and a. So let's do a substitution. Now, if h is x minus a, then something else could be said. We could say that x is a plus h. And I see an x right here. So it's completely feasible for us to do the following. And there we go, a new formula for the slope. So we are saying f of a plus h minus f of a all over h. Let's take a look at this on Desmos with some animation as well. So now we've got a slider for h. You can see it moving right there. If I have my original point anchored at 4, 4, just as we did last time, and I take the distance between 4 and my other point and make it larger, you see we move farther apart. If I take that value h, which is the distance, and make it smaller, my points get closer together, my secant line becomes closer and closer to my tangent line, and it becomes undefined when a and f of a plus h are the same. There we go, moving out. So this way of formulating the slope in terms of the distance between a and x is most commonly used in general mathematics. We use this formulation so much in science, engineering, and business that we give it a special name. We call this the derivative of a function. So for a function f defined at x equal to a, the derivative of f is given by f prime of a equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. And remember, this will be the same value as the limit as x approaches a of f of x minus f of a over x minus a. The reason that we prefer this formulation right here, this one is easier to calculate. Let's look at how it works. Find f prime of a for f of x equal to 1/4 x squared. What is f prime of 4? So f prime of a is asking us to perform this operation without numbers. It's saying just do it for the letter a. So that means we need to look at the limit as h approaches 0, and we're going to plug things in. So f of a plus h minus f of a over h. Okay, well in this case, the function is 1/4 x squared. So limit as h goes to 0 of 1/4 a plus h quantity squared minus 1/4 a squared over h. And let's expand up top. 1/4 times a squared plus 2ah plus h squared minus 1/4 a squared all over h. Okay, if we distribute our 1/4, I'm going to get 1/4 a squared plus 1/2 ah plus 1/4 h squared minus 1/4. That's hard to read. 1/4 a squared all over h. Now, these two terms cancel, and everything else has an h in it. That's what I meant when I said this is easier to calculate. So we can now cancel out these h's. And what we're going to get is the limit as h goes to 0 of 1/2 a, oops, I don't even need a fraction bar anymore, right? Limit as h goes to 0 of 1/2 a plus 1/4 h. And as h goes to 0, that just gives us 1/2 a. That would be the answer to f prime of a. So and that means that to find f prime of 4, we just plug 4 in for a. Which gives us 2. And yes, that corresponds to the slope that we had seen before. Good stuff. Let's do it again. Let's use a different function. Let's use f of x equal to the square root of x. Find f prime of a, then evaluate f prime of 1, f prime of 4, f prime of 9. Now, these would have formerly been arduous. We would have had to do 3 separate calculations. Would be painful, but not if we first calculate f prime of a and then plug into that new function. So f prime of a, this looks like the limit as h goes to 0 of square root of a plus h minus the square root of a over h. Okay, so as with most situations with radicals, let's try hitting this one with a conjugate and see if that helps our lot in life. A plus h minus root a. And as per our want, we are going to leave the bottom in with as little actual multiplication done as possible. So up top, we will have a difference of squares that gives us a plus h squared minus square root of a squared. Down below, as I said, do as little work as possible. This will simplify up top to give us a plus h minus a. Down below, we have the same thing we did before. And this is where we see some advantageous happenings. So that's going to give me h over h times this square root mess. And we cancel, and we get 1 over radical a plus radical a if we go ahead and evaluate the thing. That looks like 1 over 2 radical a. Okay, now we want it to evaluate this for f prime of 1, f prime of 4, f prime of 9. So we're using that expression. Then f prime of 1 gives me 1 over 2 root 1, better known as 1/2. F prime of 4 gives me 1 over 2 root 4, which looks like 2 times 2 on the bottom, 1/4. And f prime of 9, 1 over 2 root 9, 2 times 3, 1/6. Normally I would end here, but I just want to draw your attention to the fact that this is faster. While our body of work here does have a lot of writing, this was significantly faster than if we had used our old method of limits to find each of these individual expressions. And that's the reason for adopting this new notation, this new formulation of f of a plus h minus f of a over h, and for distinguishing the whole object as a derivative.